Look, if you're training large AI models right now, you already know the massive potential. But let's be real, you also know about the massive headaches involved. It can be incredibly frustrating to get it right. So today, we're diving into how you can completely optimize your deep learning workloads using NVIDIA Blackwell on Amazon SageMaker AI. I mean, be honest here. Are out-of-memory errors and forced model sharding just completely tanking your training speed? It's basically the modern-day blue screen of death for AI engineers. Most of us are constantly battling these exact constraints, forced to limit our batch sizes or cut sequence lengths short just to keep the infrastructure from crashing.
But there is a way out. Here's our playbook for today to demystify all these technical specs into actionable steps. We'll start with the AI training bottleneck, then introduce NVIDIA Blackwell. After that, we'll cover mastering memory management, picking the right precision, deploying on SageMaker, and we'll wrap up with the 14B parameter rule.
All right, part one, the AI training bottleneck. Let's set a quick baseline. Scaling large models has traditionally been so painful because it causes severe communication overhead. You basically end up stuck in this frustrating loop of forced model sharding and those dreaded out-of-memory crashes. The ideal state, obviously, is having much larger batch sizes and much longer context windows. And the most direct solution to break free from these constraints, you simply have to expand your underlying memory. Which brings us to part two. Enter NVIDIA Blackwell.
You see, Blackwell isn't just another faster chip. It literally rewrites the rules for AI infrastructure. Let's start with the number 180. That is the absolutely massive 180 gigabytes of memory available on the B200 GPU instances, which you can tap into right now on SageMaker AI. And actually, scratch that, it gets even better. You have a staggering 268 gigabytes of memory available if you use the B300. All this extra room means you can simplify or even completely eliminate the need to shard your models.
Then there's 1.8. Thanks to the NVLink 5 interconnect, you're looking at up to 1.8 terabytes per second of bidirectional GPU to GPU bandwidth. To put that into perspective for you, that's roughly equivalent to downloading hundreds of high-definition movies in a single second. It is a massive reduction in memory pressure for distributed workloads.
Okay, moving on to part three, mastering memory management.
Let's turn our first real optimization knob here. A fascinating concept to use is activation checkpointing. Think of this like a simple transaction. You pay a slight compute tax, usually around a 10 to 30% overhead, to essentially buy massive amounts of GPU memory space. Because instead of storing intermediate activations, you just recompute them on the fly. And the payoff for this is brilliant. Let's say you've got a 1 billion parameter model. Your baseline might give you about 6,000 tokens per second. If you flip on checkpointing, your memory usage drops dramatically, though you do take a tiny hit to your throughput. But here's where the magic happens. By reinvesting that freed up memory into a much larger batch size, say bumping it up to 16, your throughput completely rockets to roughly 8 times the baseline. You'd be hitting around 51,000 tokens per second. So how do you know when to actually use this? Well, for smaller models under 14 billion parameters, you generally don't need checkpointing at all. But for large models over 14 billion parameters, checkpointing is no longer optional. It is an absolute prerequisite if you want stable training. That brings us to part four, picking the right precision. This is our second optimization knob. Blackwell's 5th generation tensor cores are designed to accelerate some incredibly useful reduced precision formats, specifically FP8, MXFP8, and NVFP4. Simply put, lowering the precision increases the number of operations your GPU can run per cycle, all while drastically reducing your memory bandwidth requirements. And once again, we come back to that magic number, 14 billion parameters. For small, compute-bound models under 14B, the overhead of quantization kind of offsets the gains you'd see, so you should just default to FP8. But for large, memory-bound models over 14B, the impact is massive. You're going to want to use MXFP8 if you need strict accuracy, or jump to NVFP4 if your goal is maximum absolute throughput. All right, part 5, deploying on SageMaker. So how do we take all this theoretical stuff and practically apply it? Amazon SageMaker AI makes implementation super clear with 4 progressive steps. First, you create your fully sharded data parallel Python script. That's essentially just the code that splits your model across multiple GPUs. Second, you build your AWS deep learning container. Third, secure your capacity. And fourth, submit your training job. Now, when you go to secure capacity for those P6 B200 instances, you've got to balance cost and reliability. You've basically got two routes. You can use flexible training plans if you want predictable, continuous availability, or if your workloads are fault-tolerant, you can use managed spot training to heavily optimize your costs. You just have to make absolutely sure you are saving your checkpoints to S3.
And finally, part 6, the 14B parameter rule.
If you take just one single thing away from this explainer, let it be this: 14 billion parameters. This is the critical dividing line between compute-bound and memory-bound AI models. Understanding this one single threshold dictates exactly which knobs you need to be turning to optimize your infrastructure costs. So I'm going to leave you with a question to think about. Based on your model's parameter size, which optimization strategy are you going to deploy first on NVIDIA Blackwell? Take this framework, apply it to your own workloads today, and go start